Hi, welcome back to es346 Basic Thermodynamics. This is module 5.4 on heat exchangers. The section in the textbook is section 5.4, subsection number 4. Here are the two learning objectives for this module. At the end, you'll be able to calculate the energy transfer rate in the heat exchanger, and you'll be able to determine the mass flow rate requirements for a heat exchanger. First, I want to talk about heat exchangers and the energy balances you can do over them, because there's actually two ways you can apply the energy balance. So first, let's talk about a heat exchanger. The point of a heat exchanger is to do just as it sounds. Just go ahead and move heat from one fluid to another. And one of the things, they tend not to mix the fluids. So as this diagram shows, I've got a fluid B and a fluid A, and they don't mix. So what I have is this hot fluid, fluid B, is becoming a warm fluid as it moves through here, and I have a pipe moving through where fluid A, this is coming in cold and is coming out somewhat warm, including the warmer relative terms. So I'm moving energy from fluid B into fluid A, and that heat transfer is occurring across this cross-sectional area. Now, if I was to apply an energy balance, as I show here with this dashed line that goes around the entire heat exchanger, the heat exchange that's going on is at the surface of that pipe right there. It's not going on across my boundary. So the energy balance across this whole thing, this whole system, says that Q is equal to 0. And if I apply an energy balance this way, I don't calculate the amount of heat being transferred between the fluids, but I often can calculate what are the required mass flow rates. And we'll do an example that shows that. But there's another way I can go ahead and analyze heat exchangers. And what I could do is, instead of defining the whole thing as my control volume, I could define just the tank of fluid B, for example, to be the control volume. So what this diagram is attempting to show is just that the red section is the control volume. It's got this hole cut through it for the pipe. And in that case, there is actually going to be energy crossing the boundary. So there would be a boundary there. So there, Q would not be equal to 0. And the control volume would be just the volume of fluid B. Fluid A would all be on the outside of my system. And this works well if I want to calculate what my rates of heat transfer are using an energy balance like that. I could also alternatively just flip the whole thing and do my control volume of just fluid A. And again, I would have a Q that's not equal to 0. The direction is different. On the left-hand side, heat is leaving my system. It was leaving fluid B. On the right-hand system, it is entering fluid A. So it would depend on whether this is heat leaving my system or entering my system. But in both of them, Q would be 0. So you realize there's two different ways you can analyze it, or you could kind of say three different ways. But usually it's the whole system where Q is 0, or just part of the system where Q is not 0. It depends on what you're trying to find, or for example, maybe what you're given in your problem. That usually becomes clear when you do an example. Before we do an example, though, I want to just look at some example different heat exchangers that you could run into in industry. And so what this is here, this is a condenser. And like the name says, the point of it is to go ahead and condense a vapor to a liquid. And the way it happens is you run water through all these little pipes you can see here on the right-hand side. Usually it's water that runs through these pipes, and they tend to be cold, colder than the fluid that they're attempting to condense. And the water would come out there. So it would come in cold here and leave warm. And it's getting energy from a vapor that's tending to condense. And so I think it's on the other side of this. There would be a large inlet of vapor going into this tank that has these cold pipes in it. The water or the refrigerant, depending on what's being condensed, would condense onto them and then drip out and then go ahead and dribble out over here. So then this would be coming in hot and leaving relatively warm. That's what an industrial condenser looks like. And this is a very common thing in power plants. Here's another type of heat exchanger you'd run into in the food and beverage industry. And this is called a parallel plate heat exchanger. And they're showing here three different sizes of them. But what they are is a whole bunch of little thin plates that are sandwiched together, and these bolts just hold them together so that they don't leave. And you have a fluid that enters here and comes out on that side, and then you have another fluid that is coming in there, and you don't quite see it's coming out on the other side there. We look at the inside the way these go. So this is a blow-up fluid. Now pull that parallel plate heat exchanger apart. This is the way it looks. So you've got these plates, and they're fairly close together. And so here you're running your cooling fluid in. And so you have cooling fluid that comes in, and some of it goes up between that plate, and some of it goes up between that plate. And every other plate, some of the cooling fluid comes out. Then here's my hot fluid coming in, and it does the opposite. It comes in across every other plate. And remember, heat exchangers, the fluids don't mix. And in the beverage industry, this is pretty important. You want to keep your materials sanitary against your cooling fluid. And so what's happening is transfer is occurring across these little thin plates. You can see it's occurring from that region over there and from that region into there, going from the hot fluid into the cool fluid. And each one of these sections is getting a little bit of the fluid. If I looked at a bunch of plates kind of from the side, for example, if this was my cooling fluid, part of it going between every other plate like this, and then my hot fluid, part of the fluid coming through every other plate like that. And so the number of plates that you put in here is dictated simply by the volume of material that you want to move through or how much cooling you need to accomplish with the heat exchanger. So this would be a liquid to liquid heat exchanger. The condenser was a liquid to vapor heat exchanger. Here's one more type of heat exchanger, and this is an air-air heat exchanger. And this is pretty common in residences. In fact, this would be a heat recovery unit or heat recovery ventilation system, or HRV, where the point is you're moving air out of your house so your air doesn't become stagnant, but if it's cold outside, you want to recover some of that heat. So here we have hot air from inside the house, and it's leaving somewhat warm before it gets dumped outside. Here's the cold, fresh air, or the cold, fresh air that's coming in, and it's going to go ahead and leave somewhat warm and will eventually go into your house. And so the exchanges goes on inside this little honeycomb unit here. And what they look like, I kind of show on this diagram here. It's this sort of tessellated or honeycomb. You can imagine if this is the warm air shown in the gray and the cold air in here. Again, they don't mix, so one fluid will be going through its own channels and the other fluid going through its own parts of channels. And the heat transfer is occurring across these really thin plates. And if you remember our heat conduction equation, it said Q is equal to Ka delta T over delta X. Well, that delta X is the thickness of that plate. It's really small. So if this is really small, I get a really large value of Q. So the ideal heat exchanger is you want really thin plates. So you get really, really small delta X. We also tend to make them out of metal, so you have a high K. So you get a good rate of heat transfer. You can make a nice compact heat exchanger. All right, so now let's go ahead and do our heat exchanger problem. And this is for a condenser, and that's what the required flow rate is. So I'm going to kind of explain what's showing here. What we have is we have water coming in at these conditions here, coming in at 15 degrees Celsius and 300 kilopascals. And it's warming up to 30, so it's got a 15-degree temperature rise through the condenser. And what I have is R134A that I'm attempting to condense. And so it's at this pressure and this temperature, and it's coming out as a saturated liquid. X equals 4, so it's coming off as a saturated liquid. Now, the refrigerant, I'm given the mass flow rate of the refrigerant is 8 kilograms per second, and what I'm trying to find is what is the mass flow rate of water that's required to go ahead and condense this material. So we're going to go ahead and write our energy balance that says the rate of energy that goes in is the rate that energy goes out. And if I look at my system here, I've got two arrows pointing in. So I have a mass flow rate of water, and its energy is going to be the enthalpy of it coming in. And so let's go ahead and we've got the factor already numbered 1, so this will be times H1. And the other one coming in is my refrigerant, so that would be the mass flow rate of refrigerant, and that's enthalpy is H3. That's going to equal to what goes out, so my mass flow rate of water at condition 2, H2, and the mass flow rate of refrigerant times H4. So there's my energy balance. I'm trying to find the required water flow rate, so I'm trying to find MW. So I'm going to rearrange this equation for MW, and MW is equal to H4 minus H3 over H1 minus H2, and all of that times the mass flow rate of refrigerant. M sub R, it's an R there. Okay. So let's go ahead and look at this a little bit more. So H sub 4 is a saturated liquid, so that's H sub F at 800 kilopascals. So that value right there at H4 is going to be HF of the refrigerant. And then I've got H3. So here are my conditions of H3. I'm given a pressure and a temperature. This is actually superheated, so I'll end up looking up H3 on the superheated tables for refrigerant. And now I've got water at 15 degrees Celsius and 30 degrees Celsius This pressure is much above saturation pressure. So what I have is a compressed liquid here. So I can approximate this as an incompressible material. So I'm going to approximate that as Cp T1 minus T2. So I can go ahead and start putting in values into this now. So I'm going to look up my refrigerant values off the table. So this is 95.47 minus 306.88. That's the superheated refrigerant. It's the 306 number. 95 is the HF value. Heat capacity of water, it's about 4.2 kilojoules per kilogram degrees Celsius. 4.2. All right. And then my temperature change, I've got H sub 1. That's 15 minus 30 for my temperature change. And that's all multiplied by my 8, the mass flow rate of my refrigerant, 8 kilograms per second. So we'll go ahead and do that arithmetic, and that comes out to be 26.85, and my units are going to be kilograms per second. So there's the required water flow rate in order to condense that much refrigerant. Okay, here's a different problem we're going to do. It's another, again, a heat exchanger, but we're going to be looking at an HRV unit here. And it asks to find what's the outlet temperature. And so here's like my hot air coming in from the house. It's coming in at 70. And I want to know what it's leaving the recovery unit at. This is the outside temperature coming in cold at minus 20, and it's leaving at 50. So again, I'm going to go ahead and write my energy balance. It says that the energy in is the energy out. And so I'm going to have, in terms of my numbers going in, I have M1, H1 goes in, and M3, H3 go in. The two arrows going out are 2 and 4. So M2, H2 plus M4, H4. And those are mass flow rates. So a couple of simplifications here. I can realize that if I'm moving my air, right, so the mass flow rate of 3 has to equal 4. So the mass flow rate of 3 has to equal the mass flow rate of 4. And then the same thing with the cold air, for it to be conserved. The mass flow rate of 1 is equal to the mass flow rate of 2. And with a heat recovery unit in your house, you bring in just as much mass as leaves. Your house remains at steady state, otherwise you drain your house of air, or you fill it up with air over time. So those are actually all equal. So I can actually cancel all those mass because all those numbers are the same. So what I end up finding out now is that I have H1 plus H3 equals H2 plus H4. And if this is air, I can replace this with Cp. So Cp_T1 plus Cp_T3, Cp_T2 plus Cp_T4. And over this temperature range, heat capacity is pretty constant. I can cancel those terms, and I end up finding out, not surprisingly, that what my outlet temperature is going to be, well, if I have a 70-degree temperature rise in cold air, I'm going to have a 70-degree temperature drop in the outlet. And so T4 is going to be equal to 0 degrees Celsius. So that's the temperature that leaves after the heat recovery unit. So it went in at my nice balmy, oops, sorry, that's Fahrenheit. Went in at my nice balmy 70 degrees Fahrenheit, and it dropped down to 0. So I was able to extract a lot of energy from it. What would be nice to know is what's the cost savings of the HRV value. So the whole point of putting these in is that you want to go ahead and save energy. So kind of give ourselves a ballpark number of what that might be. So what I want to do now is I need to quantify what the amount of heat is. And the amount of heat is going to be M times delta H, which for my ideal gas is going to be my mass flow rate of air, Cp times delta T, where that's at 70 degrees I just calculated for. So I need to know how much mass is moving through, so for example, in a particular period of time. And there's something that's called the air exchange rate, or ACH, or air change rate. And this is the number of volumes of air that changes per hour. So if you have your house that's well sealed up, they recommend, so the air doesn't become stale, that this whole volume of air gets moved through here some certain number of times, and it's reported on it per hour. So a common value for a house might be 5 volumes of your house per hour. Okay? So that would tell us how much material is moving through. So we'll use this average value of 5. to find out how much this HRV is going to go ahead and save us per hour if we run it. So what I need to do is go ahead and find the mass of the mass of material in my house. And well, I know the volume of an average house is, just to kind of put a ballpark number, is about 50,000 cubic feet, so it's a somewhat large house. And so if I change 5 volumes per hour, my volume flow rate through the house is 250,000. That's going to be cubic feet per hour. So if I want to go ahead and figure out the mass, I need to know the density. So I'm going to use the ideal gas law there that says PV is equal to mRT. And so if that's V dot and that is M dot, I can know that M dot is equal to M dot over is equal to PV dot over RT. There we go. We can go ahead and find out what our mass flow rate is. So I'm going to go ahead and compute that. And so I've got Q, and if I put in those values, and I'll use this 70 degrees here for temperature, converting it into an absolute, I get a mass flow rate of about 18,720 pound mass per hour. And now I need my CP value. The CP of air is about 0.17, and the delta T was 70 degrees Fahrenheit, change in temperature. So that gives me what my rate of heat per hour is, 223,000, and that is BTUs per hour. And so I'd like to know what the cost savings is. I've got it in terms of BTUs, so let's go ahead and look up the lower heating value for diesel. The lower heating value for diesel is about 18,500, and that's BTUs per pound mass. So I can now determine how many pound mass of diesel I'm doing per hour, and I find out that that ends up being equal to the mass of diesel. You divide those two numbers, is about, that's about 12 pounds per hour. And that, if you go by density, is about 1.8 gallons per hour. So you're saving 1.8 gallons of fuel per hour. And in fact, I just ordered my fuel today. It was $3.80. So that comes out to be about $7 an hour. So saving $7 an hour running this HRV unit, that's not an insignificant amount of money. And that's why a lot of people in cold climates install HRVs.